Okay, the gullet is our topic, which is the structure. Can you please turn off your uh, art video? So this is our topic today, the structure. Uh, Marij, can you turn off your video? Okay, this actually is a structure which carries pretreated water to the filter. So from this structure, water comes in and then goes into the structure. I mean the filter side for filtration. During normal filtration, it also carries backwash water and filter to wastewater away for treatment and recycling through the plant. So during when we have backwashing, also as I showed you earlier, from gullet water goes into the from wash stuff water goes into gullet, and then from gullet it goes out for treatment and recycling. So usually we use flat bottom gullet, but I showed you one video which has sloped gullet also. That was kind of a new thing or new innovation. But usually we use flat bottom gullet. Here you can see this feed is going into the gullet and through gullet into the cell in sand filtration and filtration is occurring. Or from here reject water is going also. So if you see the view, one is illustration you can see here. This is the wash trough, backwash trough, and this is the height of gullet. And then from here water goes out. So this is when water, if you can see, water is coming out to you, toward you from gullet. So it's coming out like this during backwashing. Water is coming out and falling into the gullet. So when it happens, then we get a profile of water level in the gullet structure like this. The water, this is all water, and water goes out from here. So the height of water at the site where there is no exit, that side of gullet, we call it the maximum height. We call it capital H. We can denote it by capital H. But when water will go out from the outlet, from the gullet, there will be a decline of depth. And decline of depth, the depth will vary. And this depth, variation of this depth, we can represent by the small h, the small h. And then fresh water will go out. This is the gullet crust, where the filled and backwash troughs are placed. The profile of water will be like this. And then water go out depending on the velocity profile, can be like this, can be like this, can be like this. It vary. Both capital H and small h will vary. And this one from here to here is this profile will vary according to the length of gullet. This mentioned here. Okay, the upper elevation of the capital H is actually the depth of wash water at the upstream end, which is we set below the bottom of the wash trough. So this is just below the bottom of the wash trough, which discharge into the gullet so that the wash trough's discharge is a free fall. So wash trough discharge is a free fall, and then finally this water has profile left within the gullet, inside the gullet, and water goes out. This is small, the elevation of the bottom of the gullet is variable. This is actually variable. It varies. It can be here, it can be here. It's variable. it can be at the bottom of the under drain. If this is under drain, this level can be here. It can be at the bottom of media. If media is somewhere at this level, the edge can be at that level. It can be the same elevation between the top and the bottom of the media, or it can be at the top of media. So it can be here, it can be here, it can be somewhere here, it can be here. It's vary. It will vary. So the flow of backwash water, which is coming here out of the gullet, controls the dimension of edge. This dimension of edge will be controlled by this flow. How much flow is there? And this flow, the lowest visible depth edge at the outlet of the gullet is determined by two things. One is height of height of wastewater required to overcome the entry head loss into the outlet pipe. So there is an outlet pipe, and when water goes out, there is a head loss because of friction in the entry pipe. So water should overcome this entry head loss to go out. This entry head loss can be determined using this number, or this fraction 0.7 v square upon 2g. The water should have this head loss to go out to overcome the entry factor, and the velocity head that is lost in producing the desired velocity in the pipe. So this velocity head, this velocity v, should be maintained because of the velocity head, which is actually derived. We can derive from Bernoulli equation. If you have studied Bernoulli equation, then you can remember it. So Bernoulli equation, this is the Bernoulli equation. If there is a pipe like this, and there are 2 points, one point is somewhere here, another point is somewhere here, then energy per unit volume before and energy per unit volume after, before here and after this here, energy will be equal. So if we write it mathematically, we can write like this: is energy at point 1 here and energy at point 2 here. This is total energy should be equal, and energy has some components. So the energy has three components. One is called pressure energy, another called is kinetic energy per unit volume, another called is potential energy. So at point P1, there will be pressure energy, kinetic energy, and potential energy per unit volume, denoted by these figures. Kinetic energy per unit volume is half rho v square. V is velocity, rho is density, and potential energy rho gh. Rho is density, g is acceleration, gravitational acceleration, and h is height, and so on. So this is conservation of energy should be equal to the power point. So it should be like this, should be equal. Of course, we have to consider this pressure energy. Sometime we just use as we convert into this by dividing rho g, the whole equation we can write like this. So pressure energy can be like this, and velocity energy can be like this, and potential energy can be like this. And potential energy can be represented with the elevation with datum. So if this is datum, the potential energy can represent like this: z1, and here z2. So we can write this equation. This is Bernoulli equation. It should be equal, but in real situation they are not that equal. So because of some loss of energy happen because of friction at this point, so we have to consider this loss of energy because of friction, we call it head loss. So we write like this. Anyway, this because head loss is occurring, the velocity will be different at this point and at this point. It's just brief description of Bernoulli equation. So the velocity head that is lost in producing the desired velocity in the pipe, this factor plus the entry loss, entry head loss into the outlet, these two factors determine the visible depth or small h. Usually, the backwash conduit velocity is within 1.2 to 2.4 meter per second. So this velocity is 1.2 to 2.4 meter per second. Okay, with this theoretical background, let's calculate, or let's have some more measurements. Remember this equation I showed you to calculate the capital H height, this one, which is related to variable height of water with x, with the length of conduit, and wash water discharge. Wash water discharge means water is coming from here and here and here, total wash water discharge. And of course G and B, which is width of gullet, and again this is small h, so height at different length of gullet. So we can find this capital H if we know small h, and if we know this wash water discharge. So this wash water discharge we already determined from the backwash rate and the area of the filter. Remember when we were solving the problem, last problem, we calculated wash water discharge. This water discharge we can find. Sorry. We can find this wash water discharge by backwash rate and the area of the filter. We can find this QWW, wash water discharge. Then we know this, we can select a value of a B, to calculate this value H. And this solution is iterative. You have to change and reach to the good one. Now we measure from the bottom of the wash tub. The depth is checked against one of the criteria noted above. The criteria we set above, and which are those? If the depth is greater than the depth of the bottom of the under drain, it is too deep. If depth is is greater than the depth of the bottom of the under drain, so a filter is here, and then you found the depth H here is too deep. This means it's somewhere here. From here, the water level is here, so it's too deep, so we cannot use this one. If bottom of the gullet is above the media, the width may be too large. If bottom of the gullet, so if we calculate the H and we found the bottom of gullet is media somewhere here, say media somewhere here. If it is somewhere here, then means that we selected the wrong value of B. It's too large, so we have to change. Depending on the size of the plant, with a smaller plant having smaller gullet, trial width in the range of 0.22 meter. So we start from this within this range. With a smaller plant having a smaller gullet, we start with this one within this range. So let's solve the problem. Whatever I discuss, we can try all of them to calculate. And this criteria we set, and we discuss about how to uh, use lower, how to find lower h, which is depending on entry head loss and the head loss or velocity, which or velocity head to produce the desired velocity in the pipe. Then we can find the backwash wash water, backwash discharge, and put in here and select a value of B, which is width of gullet, and then check whether where this H is coming. Either it is too deep or you selected the value of B is too large. Usually we select the value of B within this range. So let's apply this all of things in one example. This example 11-7, which says determine the gullet dimension for Ottawa Island rapid sand filter. Use the filter dimension, for example 11-5, which we already have solved this one, and the backwash rate from example 11-6. Backwash rate calculated here is 11-6. Here already it's calculated. So we have this one and data from 11-5. Now we have some more. Assume a 450 millimeter diameter pipe from the gullet is to carry the wash water at a velocity of 1.8 meter per second. We have some assumption that the velocity, the diameter of pipe of exit pipe is 450 millimeter and the velocity is 1.8 meter per second. Means that this diameter of this pipe is 450 millimeter and this velocity is 1.8 meter per second. So now we have, it means that we can calculate here this factor if we know the velocity, and also we can calculate the velocity head here. It means that we can find the h because this data is given, and because the wash water discharge is already we have calculated. So with the value of h given, we can select the value of b to calculate the capital H or big H. Okay, so the velocity is given. The velocity is given, then we can find the velocity head using this equation. V square over 2g. This is velocity head in effluent conduit. So V is 1.8 meter per second, and then G is 9.8 meter per second square, and we can put it, and we will get this number. So 0.17 meter. This is velocity head in the effluent conduit. The water should overcome this velocity head to go out. Also, if we combine it with this one, the entry head loss into the outer pipe and the velocity head, this will be 1.7 V square over 2G. It's all together. This number will be like this. So we can use this. It include velocity head in the conduit and the entry head loss together. So we have this number now, 0.28 meter. So now we can calculate dimension of a small h. The dimension of a small h are from here to here, which include the height or diameter of pipe and then more. So we have diameter of pipe, which is 0.45, and velocity head plus entrance head loss, which is both together this much. So we put here this much. The small h is 0.73 meter. We have calculated this one. Okay. And remember, we have to calculate the. So we already have calculated from example 11-5 the wastewater discharge. So we can calculate using the dimensions and the flow, which was actually 36 meter per hour, and hydraulic load multiplied by width multiplied by depth, this area, which gives, and we convert it in hour into second, so we will give 0.286 meter cube per second. So this is this meter cube per second. Remember this one already we have calculated this this figure here. Anyway, backwash velocity was 36 meter per hour. If velocity multiplied by area, and area, you remember 2.6 is 5.2 multiplied by 5.5, which we already calculated here, which is 180 meter cube per hour. If you convert it into second, we will get this number, 0.286 meter cube per second. So we have now this one, this guy, QWW. We have the small h, we have g. Now we have to just assume the value of b. So let's assume a value of 0.6 meter as a first try. So if we put this one 0.6 here, we will get the capital H value 0.8 meter. Remember, this 0.8 meter is below the bottom of the wash trough. Because the wash trough depth we calculated the total depth of the bed 0.8 meter. So this one is just below the bottom of the wash trough. This 0. We start from here. Okay, we will start from here. Then we will have H. So we can have now depth is capital depth plus depth of wash trough. So start from here 0.8 plus 0.8, then plus this one. So we will have total depth. So this is H we calculated, and depth of wash trough also we have calculated in last example. Depth of wash trough here. This is the depth of wash trough. It's 43.5 centimeter. Now you can convert it into meter. So you can convert it to meter. We can put it here. So this is the total depth, which will give 1.235 or 1.25 meter below the lip of the wash trough. So this is wash trough and this bottom. So we can have this is lip. This total is 1.25, and here this will be H, capital H, this is 0.8 meter. Okay. Now we check the depth using the height of backwash trough as we estimated in the example 11-6, and the standard depth of sand, gravel, and underdrain block. So we use these things. The height of wear edge above the undisturbed media is 0.8 meter. Means this is media. We calculated in 11-6, and here is water. This height is 0.8 meter, and we use standard depth of media. So sand, blah blah blah, sand, gravel, sand, gravel, and the underdrain. Standard depth sand is 0.6 meter. Standard depth of gravel is 0.3 meter, and the depth of underdrain block, we have this underdrain block is 0.3 meter. Now we try to match with this edge we calculated here with these things we have already calculated together. So let's start. The gullet is 1.25. We calculated this edge, and we have some safety factor is 0.5. So start from this height, the top of the trough to the bottom of the trough, which is 0.4. This one is about 0.4. So 0.4. Then the bottom of the trough to the top of media is also 0.4, because from here to here we calculated the height. The expanded bed height must be 0.8 meter. So it is 0.4, total is 0.8 meter. Now we assume we take the depth of sand is 0.6 meter. The total here is up to 0.6 meter, and then 0.3 meter of gravel, 0.3 meter gravel here, and then 0.3 meter of underdrain block and 0.3 meter of underdrain block here. So we will have underdrain block and gravel, and then this level will reach. Then there will be sand, and then bottom of trough, and then top of the trough, and then this is matching very well up to this level, and then we have a safety factor. So our assumptions of selecting B were okay. If anything, if this thing comes, this edge comes somewhere here, or here, or here, then we have to change the B value of B. So before going further, I want to stop recording, and I want to ask you if you have any questions. So let me see if I